All right, let's try to run through these next problems a little bit quicker. So example 2 right here, we need to solve for the value of x that makes this whole equation true. Okay, so how can we go about doing that? Well, let's play around a bit with the logarithm properties. So one logarithm property that we know, and one thing that might make this whole equation simpler, is the product rule for logarithms. We can group these two logarithms together into one logarithm. Maybe that simplification will tell us where to go. So we'll do log base 3 of what? Let's do square outer brackets. We are going to collect the input of this first logarithm and the input of this second logarithm. How do we collect them? We collect them as a product. So we multiply them. And then that's equal to 1. So that's just an application of the product rule there. All right. Now, is there anything that I can do at this point? Well, one thing I can do actually is, just write this in a different color. I can turn this into exponential form. I think I'm sensing that that would be a good way to go, because if I do base 3 to the power 1 equals x times x plus 2, then nothing complicated would then be in an exponent or in some trapped inside some as the input of some log function or anything. And so here I'm just, again, changing this logarithmic form to exponential form. Base 3 to the power 1, base 3 to the power 1 equals the input of the logarithm, x times x plus 2. Now it's at this point that I also want to actually make note of something that I should have earlier. So if we look at this input and we get some sort of solution for x, we better make sure that our solution is greater than 0, because the input of our logarithm is defined to only be positive numbers. So if we do find a solution that is 0 or negative, we have to reject it. We can look at this other input as well. We can say, well, hey, this input also has to be positive. And what value of x would make that so? Well, if we subtract 2 from both sides of the inequality, x would have to be greater than negative 2. But this is more restrictive, right? So let's say I found an answer of x equals negative 1. That would satisfy this restriction, but it wouldn't satisfy this restriction. So really, this restriction doesn't really matter. It's in a sense embedded within this restriction anyways, right? So this is really the only restriction that matters. So I will just keep that off to the side, and if we get a 0 or negative value for x, then we'll have to deal with it then. All right, so again, I'm in my exponential form, and you know what? This is really just a quadratic equation at this point, which we can solve, right? We could solve quadratic equations like this in pre-calculus 11. So let's do that. 3 equals x squared plus 2x. Let's subtract 3 from both sides. So if we subtract 3 from both sides, we get this quadratic expression on the right-hand side that we can factor. So two integers that multiply into negative 3, but add to positive 2. Just oopsie daisies. Just double checking here. 3 times negative 1 is negative 3. 3 plus negative 1 is 2, so that works. So I get two solutions here. One solution is that x equals 1, and the other is that x equals negative 3. And because of this restriction, I have to reject this one solution. And I could try actually, I won't do this with every question, but I could try plugging it back in and seeing if it works. So let's try that. So the original statement is log base 3 of x plus log base 3 of x plus 2. So I'm just trying to verify whether or not my solution is correct here. It's a good thing to do on a test or even on your homework. So our solution is x equals 1, so let's plug that in. Everywhere x used to be, we will substitute that with a value of 1. And let's simplify. So log base 3 of 1 is 0, plus log base 3 of 1 plus 2. What's 1 plus 2? 1 plus 2 is 3. So 3 to what power is 3? 3 to the 1th power is 3. And then this is a statement that looks pretty true. If I add 0 to 1, is it still 1? Absolutely. The left side is equal to the right side. And so this is verified. So this sort of verification process is good because it tells you that you're on the right track. But we already saw that if we tried to plug -3 in, we'd actually run into an issue because all of a sudden we'd have a negative input for a logarithm, for which it's not defined. So let's look at this next example. So we have log of 14 minus log of x minus 5. By the way, let me circle my answer here. That's what I was wondering. Okay, I knew I was missing something. Circle your answer. All right. So this next example here, we have log of 14 minus log of x minus 5 equals log of x. Some value of x we could plug in here to make this equation true. What value of x might that be? Well, let's play around with this a little bit. First of all, one thing we can do is we can look at this difference of logarithms and apply the quotient rule. So I'll just write that off to the side. I didn't before when we applied the product rule, but let's try to keep track of what we're doing here. So I'm applying the quotient rule. I take a difference of logarithms, and I write their respective inputs as a quotient. There we go. And on the right-hand side, I just have my log of x. This is log base 10, by the way. No base is written, so it's log base 10. And oh hey, I can apply this log rule. Maybe I'll make a note of that in red. We know that log base c of x is equal to log base c of y if and only if their inputs are equal. So this logarithm is equal to this logarithm if and only if this input is equal to this input. So those inputs are equal. 14 over x minus 5. If these inputs aren't equal, then this isn't even true. And I am suddenly struck by the fact that I did not write my restrictions either. So here we have our input of our logarithm. It must be positive. The input of this logarithm states that x minus 5 has to be greater than 0. Therefore, x has to be greater than 5. Which of these two restrictions is more restrictive on the number line? Well, if I look at x equals 0 and x equals 5, so if we look at this restriction, it cuts off all of these values, including 0 itself. And if we look at this restriction, x must be greater than 5, it cuts off all of these values. So clearly this is more restrictive, right? It cuts off values here that the x is greater than 0 restriction doesn't even cut off. So we always take the restriction that is most restrictive out of the two options. So let's keep track of that restriction on the side there. X must be greater than 5. And here, if I want to solve for x, all I have to do is get rid of the variable on the denominator here. How can I do that? I can just multiply both sides by that denominator. There we go. The factors cancel. I no longer have a variable on my denominator, but I have to do the same thing to both sides. All right, and now again, I just have a quadratic. By the way, x minus 5 on the denominator here, we have a restriction of x can't be equal to 5, but that is already, again, taken care of here. All right, so just simplifying, we have x squared minus 5x, and then let's subtract 14 from both sides. So now we have 0. All right, so here we can just factor. we need two numbers that multiply into negative 14, but add to negative 5. That'll be minus 7 and positive 2. And from this, we get two solutions. X equals 7 and negative 2. But hey, due to this restriction, we have to reject this solution. So this is our answer. And just make it clear. If it weren't clear enough from the circle and strike through, we'll write reject and underline it just to be sure. So there you go. There's the solution for this particular question. I won't plug it in and verify it. You can try that yourself if you like. And in the next question, we're going to be doing a doozy. So I look forward